This video will show you how to simplify radicals. Let's start out with a few examples. The first example is a negative square root of 64. In order to figure out what this equals, we need to think about what two numbers multiply together to equal 64. If we think about it, that would be 8 times 8. 8 times 8 is 64. So the square root of 64 equals 8. But notice we have the negative in front. So if we put a negative in front on both sides here, that square root equals negative 8. Now let's look at a cube root. The cube root of 125. We need to think about what numbers multiplied by itself will equal 125. We have to have the same number multiplied by itself 3 times. If we take a look at that, that would be 5 times 5 is 25. Times 5 again is 125. So this cube root of 125 equals 5. Now we'll look at a square root with a negative underneath. We can never take the negative underneath of a square root because we need to think about what times what equals negative 16. Again, this number must be the same in the blanks. If we have 4 times 4, well, that doesn't equal negative 16. If we thought about negative 4 times negative 4, that does not equal 16 either. So this problem will have a non-real answer. It's called an imaginary number. Taking a look at the next square root, we have the square root of 3 squared. 3 squared is 9, so we're really taking the square root of 9 here, which is equal to 3. A lot of times we can think about the square root and the squared canceling out, and you just get the number underneath. Alright, taking a look at this problem, the next problem is a square root of negative 5 squared. If we square root this problem, we have 25 underneath, which is equal to 5. The first property says if our index of our root, which is m here, is the same as the power of a variable or a number, then that equals the absolute value of x if m is even. It just equals x if m is odd. We don't have to worry about the absolute value if we have an odd root. So taking a look at the square root of x squared, using our properties, we know that a square root has an imaginary 2 here for the index. So we're looking at an even index. So by the rule, if m is even, then that equals the absolute value of x. Here on the next problem, we have an even root and power. So again, that will equal the absolute value of y. And the next example, we have odd roots and powers. So that just equals x by our rule here. Now we'll use these rules in order to simplify these two square roots on the right. Let's look at the first one. The easiest way is to break this down into powers of the root. So the root we're looking at is 2. So let's separate this out into powers of 2. So this would be 5 squared is 25. X cubed can be broken up into x squared times x. And then we have y squared. So I'm trying to write down all the powers of 2 with each term. So if we look at this, 5 squared, taking the square root of this would be just 5. Taking a look at x squared with a square root, that will give you the absolute value of x. We'll leave this x here, and then the y squared with the square root will give you an absolute value of y. So our x to the first power will stay underneath our root. So this will equal 5 times the absolute value of xy times the square root of x. Notice that we're taking out the powers with 2 here, and they're taken out of the radical with absolute values because of our property. Now let's look at the next problem. This is a cube root, so we're looking at an odd root, so we don't have to worry about absolute value here. But again, I'm going to separate it out into powers of 3. So we'll think, what to the third power will equal 8? Well, that would be 2 to the third power is 8. And then we have a cubed. Then I'll break up the b into powers of 3, so that would be b cubed and b cubed. And then c to the fifth can be broken up into c cubed, and then we'd have c squared left over. So we'll take out these powers of 3. So the first term will give us 2. The next term will give us a. The next term is b, and another b here. And then we'll have a c. And then underneath this cube root stays c squared. Now combining these like terms, we have 2ab squared c times the cube root of c squared. Now we're going to look at reducing square roots. When we reduce square roots, we need to think of perfect squares. The perfect squares are numbers that we know the square root of. For example, 1, the square root of 1 is 1. 4 is another one, the square root of 4 is 2. Square root of 9 is 3, and so on. So we're going to try to break up numbers underneath our root with perfect squares. So let's look at the square root of 18 first. What perfect square goes into 18? Well, that would be 9, and 9 times 2 is 18. So we could separate this out and write the square root of 9 times the square root of 2. But we know the square root of 9 is 3, and we do not know the square root of 2 off the top of our heads, so we're going to leave that alone. So our simplified form would be 3 times the square root of 2. The square root of 20 is next. Think about what perfect square would go into 20. Well, 4 times 5 is 20. So we could separate that out into the square root of 4 times the square root of 5. The square root of 4 is 2. And I don't know what the square root of 5 is. So we'll write 2 square roots of 5 for the answer. Next we have the square root of 32. We need to look at the highest perfect square that will go into 32. That will be 16. 16 times 2 is equal to 32. So we'll write the square root of 16 times the square root of 2. The square root of 16 is 4. So we have 4 times the square root of 2. Finally, we have the square root of 96. So we're trying to find the perfect square, the highest perfect square that will go into 96. That will be 16 times 6. So we'll break this apart into 2 separate square roots. So that will give us 4 times the square root of 6. So you can see how we can use perfect squares in order to simplify numbers underneath the square root. There are a few other properties of square roots. One property states that the square root, or any root for that matter, can be separated out into the square root or root of the numerator divided by the root of the denominator. And the other property shows that a root in power can be changed to the power on the outside of the root. So looking at these examples, we want to find the square root of 9 over 25. To figure that out, we'll divide the square root of 9 by the square root of 25. The square root of 9 is 3, and the square root of 25 is 5. So that's equal to 3 over 5. On the next problem, notice that we can divide right away. 250 divided by 10 is 25, so we could write this, and that's equal to 5. The other problem, we could not divide those directly. These two examples use this property above. We're going to rewrite these using this property and take the power on the outside of the root. So here we could write the cube root of 8 all squared. Think about what number multiplied by itself 3 times will equal 8. 2 times 2 times 2 equals 8. So the cube root of 8 is 2. And when we square that, we have the number 4. The next problem, we have the square root of 16 cubed. Again, I'm going to use our property and write the square root of 16 and bring the cube out. I know the square root of 16 is 4, and when I cube 4, I get 64. Finally, we have 2 more problems we'll look at. These problems involve simplifying these fractions with square roots. So looking at the first, let's focus on the numerator and break down 32 into a perfect square. Okay, so we have a square root here. We're trying to figure out the perfect square that will go into 32, and that is 16. 16 times 2 is 32. And then I'll break up these variables with powers of 2 because we have a square root. So x squared will be fine, but then y to the 6 will be broken up into y squared times y squared times y squared. Remember, if we add up these exponents, that will equal 6. Alright, now I'm going to do the same thing with the denominator. We have a square root there. So we'll think about 12 and see what perfect square goes into 12. That is 4 times 3 is 12. And then I'll break up these variables into powers of 2. So a cubed can be written as a squared times a. And b to the 4th is b squared times b squared. Now we'll bring out our numbers. The square root of 16 is 4. I don't know what the square root of 2 is, so that's going to stay here underneath the root. The square root of x squared is the absolute value of x because it's an even root. Now the square root of y squared is the absolute value of y. We have another absolute value of y and another absolute value of y. And we have the square root with 2 underneath. Now let's do the same thing for the denominator. The square root of 4 is 2. I don't know what the square root of 3 is, so that will stay underneath the root. The square root of a squared is the absolute value of a. This a will stay underneath the root. And then I'll bring out these b's and have the absolute value of b for each term here. So what we have underneath the root is 3a. Combining everything together, in the numerator we have 4, and our absolute value is x inside, with y to the third power times the square root of 2, divided by 2 times the absolute value of a, b squared. Alright, now since b is squared, it doesn't have to go in the absolute value. Any number squared is automatically positive. So therefore we don't need an absolute value with that. And then we had the square root of 3a. One more thing we could do is divide 4 and 2. So that will equal 2 absolute value of xy cubed square root of 2 divided by absolute value of a, b squared square root of 3a. Now we'll take a look at a cube root. The cube root will work very similar to the square root, except we don't have to worry about absolute values. So let's break this down. I'm going to separate this out into 2 separate cube roots. Notice nothing can be divided right now inside the root. So we'll separate this out like this. Alright, now I'm going to break these variables down with powers of 3. So we have the cube root of 2x y cubed. Now the z to the 4th can be written as z cubed times z. Same thing for the denominator. 27 can be written as 3 cubed. 3 times 3 times 3 is 27. A to the 5th, I need to write that in powers of 3, so that would be a cubed times a squared. And then b to the 6th would be b cubed times b cubed. Now we'll bring out these third powers. So this will equal, well, the y will come out, so that would be y. The z will come out here, and then everything else will stay underneath our cube root. Now we'll look at our denominator. These third powers will all come out. So I have then 3, a, b, and then b. And underneath this root stays a squared. So our final answer will be to combine our like variables. That'll give us a b squared right here. And that will be our final answer.